Today's traditional avionics systems consist of separate power and data networks. This leads to a significant amount of cabling within the aircraft. The trend towards the more or even all electric aircraft means that the number of electrically controlled systems within the aircraft is increasing. Therefore, a means is required in order to reduce the overall amount of cabling in the aircraft. One potential solution is power line communications, abbreviated here as PLC. With the PLC approach, data is transmitted over the existing aircraft power distribution network. The data network may then be completely removed. PLC components are integrated into application devices, and therefore a single connector is provided for both power and data. PLC has the potential to provide a significant reduction in aircraft wiring weight and volume. Also, the absence of the data network reduces the complexity of the overall wiring and means that less wire routing must be performed. The necessary maintenance will also be reduced. The use of PLC within the aircraft does not come without challenges. PLC must provide robust communications over a medium that has not been designed for data delivery. Power distribution network wiring is unshielded, highly asymmetric, and often ramified. Therefore, PLC cannot expect the same communications channel available to a dedicated data network such as Ethernet or CAN. The PLC channel will be highly frequency selective due to reflections occurring at impedance discontinuities. The sample PLC channels shown here show the distinct notches or regions of high attenuation due to these reflections. As the channel is also dependent upon the topology and load conditions, the channel will vary from location to location, even within a single network. The application equipment attached to the power distribution network will also generate transient noise. The lack of shielding in the power wiring makes the power network highly susceptible to externally coupled noise sources such as HERF or lightning. Compounding all of these issues are the strict electromagnetic compatibility guidelines regulating the environmental requirements of all electronic devices within the aircraft. Emissions from intentional PLC signals must adhere to the same limits as all other devices producing unintentional emissions within the aircraft. This limits the transmission power of the PLC signal. Nevertheless, these challenges are nothing new for PLC technology and exist in many other application areas. PLC technology has been developed and optimized for such environmental conditions for over 15 years now. Advanced digital signal processing (DSP) techniques at the physical layer of the communications protocol are an integral part of the PLC solution and the means by which many of those problems may be mitigated. The PLC physical layer has been designed to cope with the fact that part of the spectrum of the PLC signal may be severely attenuated, provide robust communications even when the power of the received signal level is not much more than the noise power, mitigate short-term noise transients that may occur, operate even when very strong narrowband interfering signals may be present, such as is the case with HERF. Enabling this are several advanced DSP techniques, such as forward error correction, in which redundant bits are added at the transmitter in the form of coding in order to help detect and correct errors at the receiver. Orthogonal frequency division multiplexing, in which the overall signal is transmitted upon multiple subcarriers. This means that regions of high attenuation will only affect a small portion of the transmitted signal rather than the complete signal. Using scrambling and interleaving allows the influence of noise bursts to be reduced. Also, channel estimation and synchronization allow the receiver to synchronize to the signal from the transmitter, even though they both have asynchronous clocks. It is these techniques, among others, that provide for reliable communications, even in the harsh environment provided by the aircraft power distribution network. Similar to the traditional avionics architecture, the necessary components enabling PLC may be integrated directly into the application devices. This approach can provide maximum weight savings. There are two main components as part of the PLC solution. The coupling module consists of passive analog components, and its job is to couple the high-frequency PLC signal onto the power line. It also filters and protects the modem from the low-frequency power signal. It may be considered as the one component that is dependent upon the characteristics of the power distribution network. However, generic couplers may be designed which support a variety of different power networks. The coupler also provides protection circuits against transients, lightning and HERF. A critical part of the coupler design is to ensure that the performance is not highly sensitive to the impedance conditions of the power line, as those may vary widely between different points on the power network. In addition to the coupler, the PLC modem consists of two main components: a protocol chip, or even chips, upon which the PLC protocol is realized, an analog front end, which provides digital and/or analog conversion and signal amplification. The protocol chip then provides one or more interfaces to the application host processor, providing data transmission services for the host. Investigations into the use of PLC for avionics applications are not new. The University of Lucerne has been involved in two previous EU research projects which have investigated the use of commercial PLC technology for avionics applications. The first project was the FP6 ECAB project, which demonstrated the use of PLC for the in-flight entertainment system. This was a basic demonstration of the use of PLC for a high bandwidth application by delivering power and multimedia data to passenger seats over the 115-volt AC cabin network. The second project was the FP7 TAUP project, in which an extensive feasibility study on the use of PLC for commercial aircraft was performed. The cabin lighting system and cabin communication system for the Airbus A380 served as reference systems for this investigation. No principal showstoppers were identified, and the verification work within the project showed that the technology readiness level of 4 was achieved. An analysis of the developed PLC solutions showed that a 30% saving of the wiring mass could be achieved. Furthermore, relevant EMC testing according to DO 160F was performed, and the solution was shown to be compliant. However, as with other technologies, certain deficiencies were identified in the application of commercial PLC technology to the avionics environment. Commercial PLC technology has been developed for consumer in-home networking applications, which makes certain aspects of the technology not suitable for more real-time applications. Unfortunately, the relatively small avionics market size compared to the consumer market leads to unattractive conditions for the commercial technology suppliers, and therefore there is a general lack of support for providing an optimized solution for avionics systems. Due to the lack of support from the commercial PLC technology suppliers, the University of Lucerne has been developing a PLC solution for safety-critical, real-time applications for the past 3 years. This PLC protocol targets not only avionics, but also applications in which the requirements for the data bus are similar, such as electrical grid monitoring and automation and vehicular communications. The PLC protocol is based on existing industry standards, however with optimizations for the targeted application environments. Several features are provided which differentiate this solution from the available commercial solutions. Robust transmission with physical data rates up to several tens of megabits per second. Bus arbitration based on a deterministic protocol. Peer-to-peer architecture with no single point of failure. Stateless connections minimize setup and recovery times. Multiplexing of multiple data services onto a single bus. Optimizations for delivering small frame sizes with low latency. Advanced error detection schemes increase data integrity. Signal transmission techniques designed to minimize emissions and improve susceptibility according to the RTCA DO160 requirements. Operational frequencies are configurable. The University of Lucerne is a partner within the Ashley project and is responsible for providing a PLC resource within SP4DME platform technologies and resources development. The PLC resource will be provided as a series of prototypes for the purpose of demonstrating communications over a power network for the ventilation control system. A single solution supports data transmission over both 115-volt AC and 230-volt AC variable frequency, 3-phase power networks. The provided PLC coupling module, which is suitable for high power applications, supports currents of up to 10 ampere on those networks.